Gotcha. Let's party. We are recording.
Yeah. Okay. That's good. Okay. Hi. So this is module 14. So module 14, many of you may have not seen it in a workshop yet. That is because you may be going over this week. I know I'm going over it this week. So module 14, this this module will be seen at molecular geometry and electronic geometry. So molec geometry, and I'm gonna move this here. Actually, I didn't want to say it. And electronic geometry. So if you guys see at the very back of your periodic table, in the back side of your periodic table in your workbook, you may notice that there's a graph or a table, sorry. That table you will have to memorize. Can I get a yes or like, do you give me a yes if you guys found the table?
Yeah, it's in the back of the one book.
Yeah.
Yeah, it should be on the back side of your periodic table. I'm gonna look for one in Google just in case.
Yeah. So that you will have to memorize completely. I know it looks like a lot, and there's no easy way to get around it. Honestly, it's mostly just memorizing. The way I found it to be easiest to memorize that table in the back is practicing it and rewriting it over and over to the point where it's just becomes second nature. But we will be using that very much. So recently, what you guys been looking at is Lewis structures. You guys have been working with Lewis structures and drawing them and setting them up, but there is a proper way to draw the Lewis structures. So that can someone tell me what molecular geometry is? I'm misspelling things.
It's just me in the chat.
Okay. What does molecular geometry pertain to?
Well, it's just how it's gonna look, no? Anyway, once you do the structure.
Yeah, so molecular geometry is the 3D arrangement of the molecule. That's the best way to explain it. It's the 3D arrangement. Okay, and then, oh, sorry, I should probably keep chat open. Yes, this is the last review. Okay, Godina's got it, never mind. So yeah, it is the 3D arrangement of a molecule. So let's go ahead and do water. Water is a pretty good example of a molecule. So how does the water molecule look like? How do we typically draw a water molecule? You guys
There's
can give
an
me
oxygen in the center, and then
yeah, so an oxygen
and then two hydrogens.
Okay, and what else am I missing? I'm missing one vital portion to my oxygen molecule.
Is it a double bond somewhere?
Not a double bond.
The charges?
Not our charges. How many valence electrons does H2O have total? How many total valence electrons?
8.
8, yes. 8 valence electrons.
You're missing the 4 electrons.
Yes, I'm missing 4 electrons. And what are they?
On oxygen.
Yes, they're on the oxygen. These are what we call our lone pairs.
Why did you place them there though? Because hydrogen can only have one, huh? Okay.
Hydrogen can only make one bond. And yeah, that's the main reason why hydrogen can only make one bond, and it can't fit any more electrons. Okay, so these little things we'll call lone pairs. And then this section here, in your graph, it falls under the name of bonded regions. If you guys are following your graph, this is bonded regions. So how many lone pairs and then how many bonds do we have on our oxygen atom?
2 and 2.
Yes, 2 and 2. It helps if you guys circle it. If you guys notice, I always circle my lone pairs and my bonded regions. That will help you identify how many you have of each. So we have 2 bonded pairs, 2 bonded regions, and then we have 2 lone pairs. And then looking at your graph, what type of molecular geometry does this molecule have?
Linear?
Yes. Well, not linear. If it helps, what's our magic number? Our magic number is the sum of our lone pairs plus our bonds, our bonded regions. So what's our magic number here?
4.
4.
It's
So
I know it's still supposed to be bent.
yes. Yeah, that's exactly right. Our molecular geometry is bent. So if it's bent, what would be the proper
both H is supposed to be like a little over. Supposed to have a 105 angle.
Yes. So we're supposed to have kind of like a bent angle, basically. Can someone tell me why we have a bent angle?
Because those electrons are pushing the hydrogens.
Yes, our lone pairs here are pushing these hydrogens down. That's the reason why it's bent. And this is the proper drawing of our molecular structure. So molecular geometry is simply the 3D arrangement of our molecule. Okay, I'm guessing you guys want to do more examples, right?
Yes, please.
Okay. Shoot, I need to think of more. Let's do NH3. So NH3, that's ammonia. First of all, how many valence electrons do I have?
You got 3 for hydrogen. And 5, so you got 8.
Yes. So that's 8 valence electrons. So we have 8 valence electrons. And then how would I begin drawing my molecule?
Well, N is your ground. Then 3 H's. And if you want, well, this one page on 277, it helps you with the visual, I guess.
Oh, sorry. Let me open the book.
They have like a
yes.
template.
Yes.
The table thing?
Yeah, that one helps a lot too. 277 gives you a good visual. And then what else am I missing on my Lewis structure?
The 2 electrons on nitrogen.
We have 2 electrons on our nitrogen. Okay. Now let's go ahead and see our lone pairs and our bonded regions. So how many lone pairs do we have?
2. Well, 1.
1. So we don't count each electron. We just count the pair. So 2 electrons, that's pair. And then how many regions do we have?
3.
Yes, 3. Okay, so we have 1 and 3. So what does that make our magic number?
5.
5?
4. Sorry.
Yeah. 4. Yes, there you go. Okay, and then so what would be our molecular geometry? If you follow your table.
Trigonal
pyramidal. Yes, trigonal pyramidal.
I see you in the chat, Jasmine.
Oh, thank you.
We're proud of you.
Thank you. Sorry, I'm not paying attention to that. But yeah, trigonal pyramidal. That is our molecular geometry. And then now let's go ahead and define what our electronic geometry is. So what is our electronic geometry?
Tetrahedral.
Oh, sorry, no, the definition of electronic geometry. right now we'll go ahead and look at what our electron geometry is for these molecules.
Definition, I have no idea.
What does electronic geometry consider?
Is it lone pairs?
Yes. So here in electronic geometry, we are looking at how our lone pairs affect our geometry. So lone pairs affect so looking at ammonia, what would be our electronic geometry?
Tetrahedral?
Yes, tetrahedral. And then what about our electronic geometry for water?
Trigonal planar?
Our magic number is 4.
Not the same thing?
Yeah, the same. It's tetrahedral. Typically, whenever you see anything with 4 regions, electron regions, that's when you have the tetrahedral. So how would we properly draw nitrogen? How do our hydrogens look like? Let's see.
And like it's like
They're
380,
like
but like
downwards.
not like perfectly 90. Yeah.
Yeah, so it's kind of pushing it down, right? So that's the effect that this lone pair has on these hydrogens. Sort of pushes the molecules down. Okay, this is another example.
Can I ask something real quick before you move on? Why do they spread out the way that they do? Like, what's the name of the rule that we use to describe this?
What's the theory? What's the theory, guys?
Is it theory?
Yeah.
On 270, if you guys want to read it.
Gosh darn, I'm just kidding.
Is it VSEPR, something like that?
Yeah,
Yes,
the VSEPR.
You got it. Yes, ma'am.
Also, if you're feeling lazy, you can pronounce it Vesper.
Vesper.
But yes.
Whisper. Right.
Okay.
That there.
Oh, sorry.
Oh, right. No, you're good. You're good. Keep going, Diego. This is your moment.
Oh, okay. So I'm guessing you guys want more practice, right? Let's go to clear drawings.
Yes.
Can someone give me a molecule?
Let's do carbon dioxide.
Okay. CO2. So CO2. So carbon, and then I have 2 oxygens, and then how are the oxygens bonded to the carbon?
Double bond.
My double bonded oxygens, and we have 2 lone pairs on each. Okay, and then, okay, so now, first of all, am I looking at the carbon or am I looking at the oxygen? Which one am I looking at?
Carbon?
Yeah, I'm looking at my central atom, my carbon. So looking at my central atom, how many lone pairs and then how many bonded regions do I have?
You got 4 bonded? Well, 1. So you got 2.
Yes, so we have 2, yeah. So we don't count double bonds as 2 bonded regions because technically here it's still 1 whole bonded region. So we have 2 bonded regions and then 0 lone pairs because there's no lone pairs on our carbon atom.
Think of
Okay.
bonded regions as when you're bonded to different things. So even though you have a double bond, yes, there are 2 bonds there, but they're bonded to the same thing. So it's still just 1 bonded region.
Also, why are we looking just at the carbon right now? Like, why did you get the numbers just from the carbon?
It's the
Because
central
when
atom.
when we're determining the geometry of a molecule, we're only interested in what's around the central atom. That's why we don't
Oh.
care what the oxygens have.
Okay,
Sometimes
thank you.
they might ask you for the geometry around a certain atom if you have a much
Complex
bigger
molecule.
a more complex and bigger molecule. So you're gonna focus. But if you're not told, hey, focus on this specific molecule, like for example in these more simple ones, you're gonna focus on the central atom.
That I would say, like, whenever you guys are asked about like what's the geometry around this atom, that would be more for Chem 2. You guys don't have to worry about working with complex structures. You guys will be working with these simple Lewis structures.
Okay, thank you.
And then for our molecular geometry and our electronic geometry, what are they? And also, what is our magic number?
2.
2. And yeah, so here our molecular geometry is linear. And what is our electronic geometry? Also linear, sorry. Thank you. Awesome. Okay, let's do another one. Let's do an ion. Let's do nitrate. Nitrate is a tricky molecule. Very tricky molecule. It's not very fun to work with. So first off, how many valence electrons does nitrate have?
5 plus shit.
What about
24.
oxygen?
I'm sorry?
Oh, it's just like
24.
you kept writing, but you didn't ask anything.
Oh, sorry. Sorry. How many does oxygen have?
6.
Yes, 6. And then do I add or subtract that extra 1?
You got it.
Okay. Plus 1. And then what did he get? I'm sorry.
24.
24. Awesome. 24 valence electrons. All right. So how do I start off drawing it?
Nitrogen's your ground.
Nitrogen's my ground. My
3
center.
oxygens.
So I already made 3 bonds. So how many valence electrons do I have left?
2, 6. 18.
Yes, 18. So where do I distribute those 18?
Oxygens and oxygen.
Okay. Now, is this the most stable structure I can get?
No.
What do I have to do?
Yeah.
Another bond to oxygen.
Oh, first of all, let's determine our formal charges before we do that. So for nitrogen and then our oxygen, how do we compute our formal charge for nitrogen?
That's 3.
I'm sorry?
That's 3, no?
It has 3 bonds, yes. So what do I subtract that from?
5 minus 3.
So our nitrogen is a +2. Let me go ahead and erase that circle.
Am I
And
crazy
then-
or are we missing things on the nitrogen?
No, we're going all right. Don't worry.
Oh,
And then for oxygen,
6.
6 minus.
2, 4, 7.
So minus 1. All of these are minus 1. Okay. So if I want to cancel out a charge, what do I have to do?
Double bond.
I have to make a double bond. How many double bonds will I be making?
2. What?
Why 1?
What's
Why am I-
detergent nitrate?
Oh,
Why,
yeah.
why am I only going to make 1 double bond? Why can't I make another double bond?
Because nitrogen can't hold another one.
Yeah, if you guys notice here, if I were to add Sorry.
But isn't it nitrogen supposed to be +2?
No, once you make a double bond, it takes away one from the charge. And then if you notice, our oxygen isn't negatively charged anymore. It's not negatively charged anymore. Okay. If I were to make a double bond, does it follow the octet rule? Another double bond in order to cancel out. Does this follow the octet rule? Does our nitrogen follow?
Yeah.
Are we sure? No, why not?
No, that's 10.
Yeah, that's 10 electrons right there total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not following the octet rule. So in order to follow the octet rule, we have to make it only one double bond and leave it positively charged. It still cancels out with this -1, but we're still left with a -1. So that is why we are left with a -1 charge of nitrate. This is a tricky molecule. Is there any questions on that? Yeah, go ahead.
Yeah, I just forgot. How did you get the little -1 that you put on the outside? Where does that come from?
That comes from the overall charge of the molecule. So this -1 and this -1 cancel out, even though they can't make a bond, but we're still left with one -1. So
true.
That's why.
Because remember, we're doing -1 plus -1 plus +1. So what should that give us?
-1?
Yeah. So then what should our overall charge be?
-1.
Yeah, exactly.
Okay.
Yeah, we take the overall charge, and that's how we know what our correct charge is. Okay, that was a bit confusing. All right, now let's go ahead and do our lone pairs. And so lone pairs and bonded regions, and then also what is our magic number? So what is our lone pairs? Do we have any on our central atom?
0.
0. Okay. And then what about our bonded regions? How many do we have?
3.
Yes, 3. So 1, 2, and 3. So we have 3 bonded regions. So what does that make our magic number?
3.
3. And then what is our molecular geometry and our electronic geometry?
Triagonal planar.
Yes, I believe so. Yes, triagonal planar. Is it for both?
Yes.
Yes, trigonal planar, sorry. Trigonal planar. And trigonal planar. And I believe the proper way to draw the molecule was, it's this way? Ah, shoot, that's a hydrogen. Oh, I don't know why I drew 2 ends. Sorry, that wasn't supposed to be there. Drawing the correct molecule is very important, especially when it comes to polarity, which is what we're going to cover next right now. Okay, is everyone good? Is there any questions? No. Well, no, it doesn't really matter where you place the double bond because of resonance. It could be anywhere. So it could be here or it could be here.
And do you guys know, did we go over why resonance is a thing?
I think you guys covered resonance.
Because resonance exists because electrons don't stay still. They're always moving. So technically, we don't know where the double bond is. But for simplicity's terms, we just draw it wherever so we can visualize it. But technically, we don't know where the double bond is.
Yeah, if you guys ever get into modeling or into the higher ends classes, you guys will typically see like our double bonds will be kind of displayed with a dashed line. That's how we know.
And so aren't those like mostly for hydrogen bond?
I don't think so. I'm not sure.
What was the question?
You mean like the little dash lines?
Yeah.
He was talking about mostly like how software modeling software represents it. So it's a little bit weird. That's higher level stuff.
Yeah,
Like
you
for
guys.
higher
Yeah,
level courses,
I
you
think
guys don't
that's
need it
more.
unless you guys are like chemistry majors. In which case, well, if
Oh,
you're
it's because I saw it from one of my friends was like studying, and I kind of saw a glimpse of it, and I saw how they would have dash, and I read about it a little, and that's basically it. And I thought it was like what basically you're talking about, but I don't really know.
well,
No.
you can represent the hydrogen bonds with like dashed lines, but that's a Chem 1 topic mostly. But if
Chem 2.
you want to,
Chem 2.
Chem 2. This is Chem 1.
We'll learn about that later.
If you have to say Chem 1. Chem 2, sorry.
Okay. All right, let me go quickly over polarity, and you guys can go over hybridization. All right, so I'm gonna go ahead and clear. Is it okay if I clear the board?
Yes.
Yes.
Okay, good. All right, so polarity. What does this polarity typically deal with? Pretty much book upside
Symmetry,
down.
something like that, I think.
It doesn't deal with symmetry. What's the main moment about polarity?
How about we give them a hint?
Is it when an atom is being more electronegative than the other atom?
So yeah, it does.
Yeah.
So it deals with one atom being more negative than another. And how do we represent which atom is more electronegative than another? There's a specific arrow we use. There's a name.
Dipole.
Yes, a dipole. That is a dipole moment. So dipole, which means two poles, dipole. So this end represents your positive. This end represents your negative. And what does the dipole moment represent?
I do not know.
So a dipole moment, it does help us distinguish which atom is more electronegative. But it also, what does it show us about the electrons?
So if it's polar or non-polar, right?
That's what it tells us about the molecule, actually. So I'm gonna go ahead and write it. So here, the dipole moments helps identify the unequal, sharing of electrons due to electronegativity. Okay. And then so that tells us if our molecules will be polar or nonpolar. So when drawing the correct structure of oxygen, which is our bent structure, this is why it's important to sort of have an idea already of how the molecules look like. Who's more electronegative, hydrogen or oxygen?
Oxygen.
Oxygen, yeah. So what way do you think my arrow is going to point? Towards the oxygen or towards the hydrogen?
Towards the oxygen.
Yes, towards the oxygen. The oxygen is more electronegative and it wants to pull in its electrons. Okay, and do you guys think it happens the same on this side?
Yes.
Yeah,
Yes.
It does. Here, the same happens. Is there anything canceling out these two arrows?
The lone pairs, maybe?
The lone pairs don't really affect polarity.
I think there's nothing canceling out the arrows.
No, there's nothing here to cancel out these two arrows. So what happens is that we have one large dipole moment. So would this make oxygen polar or non-polar?
Polar?
Yeah, it makes it polar.
Polar is only if there's a dipolar moment.
Not always. There will be dipole moments present, but sometimes they may cancel out. Let's do an example in which they do cancel out.
Oh, okay. So
Okay.
just if they don't cancel out, that's when we know, right?
Mhm.
Like for
Yes.
sure it's a polar moment. I
Mhm.
mean a polar thing. Okay.
Yes. All right, let's go ahead and look at carbon tetrafluoride. So carbon tetrafluoride.
Yeah.
How will our dipole moments look like on this molecule? Who's more electronegative?
Fluorine.
Fluorine. And how is the fluorine going to have the effect on carbon?
It's gonna pull.
It's going to pull on carbon, right? So the dipole moment will pull on carbon. So do you think this molecule is polar or non-polar?
I think it's
Non-polar.
non-polar.
Why
because
non-polar?
Cancel out the
Yeah.
arrow.
You have a dipole moment going in each direction. You have a dipole moment going in each direction. And so that makes the molecule non-polar. Peer leaders, do you guys have any comments on polarity?
I don't think so.
If you guys have any comments on how I'm sort of showing them.
You
I
did
have
mention
one.
that-
You're doing great.
Oh,
Yeah,
okay.
you're doing great.
Because typically the way I do it is canceling out the dipole moments. That's it basically, right?
Yeah, exactly. That's how I usually do it too. So the way you guys can think about the dipole arrows is as vectors. So if you guys know what vectors are, or especially if you've already taken physics, you guys should be familiar with vectors, which are basically like arrows. And what happened? How do we cancel out vectors?
With the same magnitude in opposite direction, they will cancel out.
Exactly, same magnitude, opposite direction. So this is basically what's happening here in what Diego drew on the bottom. This is why we have polar bonds. So if there is a dipole going on, that's a polar bond. But polar bonds does not a polar molecule make. As you guys can see, those vectors, those dipoles are being canceled out by each other. So overall, there's no net dipole moment. So that makes it non-polar. Does that make sense?
Yes.
Yes.
All right, let's go ahead and do some more examples. All right, let me clear the drawings and then let's go ahead and do CO2 again, like we did last time. So how does our dipole moments look like here? Where is my arrow going to point for the oxygen and carbon?
Crap, where's my oxygen is more.
I'm sorry?
It should be pointing at oxygen.
Yes, it'll be pointing towards the oxygen because the oxygen is more electronegative. And then it'll be the same for this side. Now, is this a polar or non-polar molecule?
Non-polar.
No.
Yeah. Non-polar. Because we have two dipole moments that are canceling each other out. All right, let's go ahead and do one more or a couple more. This one is This is fluoromethane, I believe. So this is carbon and it has 3 hydrogens and 1 fluorine atom attached. So how does our molecules look like? How do our dipole moments look like?
Would the arrows be pointing to carbon?
Should be pointing to fluorine.
Yes. Or if we're looking at carbon fluorine, yes. Fluorine should be the driving force. I forget, does hydrogen really have much of an effect?
Carbon is more
Okay.
electronegative than the hydrogens.
Mm-hmm. So is this molecule polar or non-polar? What do you guys think?
It's more polar than non-polar.
Yeah, it is polar. It's polar. This is a polar molecule. That's mostly because of this fluorine here. Normal methane, which is CH4, is this a polar or non-polar molecule?
That's not.
Yeah, it's a non-polar molecule because your hydrogens get pulled towards the center of the carbon molecule. And they all cancel each other out, so that would make it a non-polar. Okay, nice. All right, we have 10 minutes, so if someone wants to go ahead and explain hybridization. Or is there any questions before we move on?
I think this is pretty decent. I think we're all good.
All right, sounds good. I'm gonna go ahead and clear the drawings, and then I'm gonna go ahead and stop sharing. So I can cover hybridization real quick.
I got it, guys. Okay, so hybridization. This is definitely one of the weirdest topics, and we now have 10 minutes, so I'm going to try to be brief. So hybridization is just it's taking some of the orbitals from the outer shell of a compound. So let's say, for example, carbon. Let's take, for example, methane. This is a really good example, and this is actually the one in your textbook. This is a textbook example, actually. So hybridization basically uses the outermost orbitals. So what would be the outermost orbitals for carbon? What's the abbreviated configuration for carbon?
Helium.
That'd be helium.
And 1s2, 2s2 and
2p2.
Yeah.
2p2. Okay, cool. So that means that we have. So let's draw the orbital box diagrams for these three. So we have the 2s and the 2p orbitals right here. So how do we fill these up, guys?
Well, that one's filled up, so
Okay, so we fill it up like this. Then we fill up,
yeah.
up, right? Okay, so so you see something weird that carbon does is that it usually makes these 4 bonds. It tends to make these 4 bonds because in order to make bonds, it kind of quote unquote promotes one of its electrons to one of the p orbitals. So what happens is that this creates something called hybrid orbitals, and most specifically, so hybrid. These are sp3 hybrid orbitals, which take the s orbital, so 1, and 1, 2, 3, and the 3 p orbitals with the promoted s electron that was promoted to the p orbitals. So these get combined together. they get hybridized into sp3 hybrid orbitals. So this leaves, so what does this mean? It basically leaves space here. These 4 electrons are ready to bond with other atoms, such as hydrogen. So it bonds with the atoms with the hydrogen atoms, and this is how you get 4 bonds. This is also why you have to get why carbon tends to make 4 bonds. Does this make sense so far? Yes, no, maybe so.
A little,
So,
yeah.
Kind of.
Yeah, so basically hybridization is just kind of promoting some electrons to another orbital. In this case, the s electrons are promoted to the p orbitals, and now you have these hybrid orbitals that that are available for bonding. So, and of course, this is the theory, but I'm pretty sure you guys might be wondering, if you're in a pinch and you forget all of this, and I'm pretty sure you will. It took me a while to actually understand this. And so you might be wondering, how can we find out what the hybridization of this is in a very quick way? So I like to count how many things or how many electron densities are around my central atom, which is carbon, kind of like how we did with the geometry. So S, SP, SP2, SP3. So it's kind of like counting the way I do it. So if you have one thing attached to it, that's S. If you have two things attached to the central atom, that's SP, including lone pairs. If you have 2 things attached to it, including lone pairs, if you have 2 things in a lone pair, or if you have 3 things attached to the central atom, that's sp2. If you have 4 things around the central atom, that is sp3. So S, sp2, S, sp, sp2, sp3.
You can also think of it as sp1, but we don't write the 1 exponent in this case, so it's just sp,
right,
and then sp2, and then sp3.
Right, exactly. So I can go over a different example if you guys want a few more examples. Okay. So
does you said that the lone pairs do matter, right?
Yeah, the lone pairs do
Okay,
matter.
do one with the lone pair.
Okay, how about we do water? Everybody likes water. Everybody likes to use water as an example, so let's use that one. What is the hybridization on water?
SP.
Are you sure?
I mean, it should be S.
Remember we said we also count the lone pairs, right? Because if you have four things around it, regardless if they're lone pairs or atoms, sp3, exactly, right? So this also counts. S, sp, sp2, sp3. Okay, let's try another one. Give me one. Anyone you want. You guys want.
CO2.
Okay, CO2. All right, I'm gonna draw this one really, really quick. So CO2. What about this one? What is the hybridization for this one? Oh, somebody mentioned SCCl2.
Is it for this one? You just SP.
SP, right? Mm-hmm. Yeah. 1, 2 things. So this one will be SP. Somebody mentioned SCCl2. Let me remember if I can do that one. SCCl2. The central atom is Se. Actually, let's build this one and figure out what the hybridization is. So how many valence electrons do we have for SeCl? 2.
6.
Okay, for the whole atom or for just one of the, for the whole molecule or for one?
So selenium is 6, and then each chlorine is 7. So 7 times 2, 14.
Exactly, right? Times 2. So that's 14 plus 6. What's that?
20.
20. So we have 20 valence electrons. Is this a charged molecule? Do I need to add or remove electrons?
No.
No, right? Exactly. Okay, so which one is going to be our central atom?
Selenium.
Selenium.
Selenium. All right. Okay, so how do we build the rest of this molecule?
2 chlorine.
2 chlorines around it. We make the skeleton. Okay, so out of 20, we've used how many electrons?
4.
4. So we got 16 remaining. How are we going to use up the rest of those 16?
Chlorine.
Chlorine? What are we going to do with chlorine? Chlorine.
Yeah. 6 of them each.
Okay, we're going to put 6 electrons. That means 3 lone pairs on each chlorine. So 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5, 6. That's 12 total. So 16 minus 12. How many valence electrons do we have left?
4.
4 valence electrons. Okay, so are the chlorines happy? Are we going to add any more electrons to it?
Can't you do double bond here?
They're all good.
Oh, they can't. No.
No, they can't, because they want to have, so these are, this is one example where chlorine does follow the octet rule. It likes to have it wants to have those 8 electrons around it. So it'll generally want to have, it has 7 valence electrons, so it'll just want to share with one more. It wants one more electron to complete its octet.
Actually, that we just go on selenium.
So we're gonna put them on selenium. Okay, cool.
I have a question real quick.
Yes, ma'am.
Is there any scenario where we're looking at an element that wants to have more than 8? Because I haven't seen anyone draw like one with more than 8.
That's a good question, actually. That's a really great question. Don't worry. That's a great question. I actually wanted to talk a little bit about that when we covered Lewis structures, but I think we might be a little bit out of time. Do we still have time to talk a little bit about that? That one's really interesting. And I
1 minute.
Okay, but before we go through that, I want the peer leaders to give me the okay to keep talking about it, just to wrap up.
If you guys need to go. If you're interested, you can stay. Thank you for coming. Go, Corina.
Okay, so before we move on to that, let's do what the reason why we built this CeCl2 is to find out the hybridization. So to find out the hybridization, we need to build the Lewis structure first. So what is the hybridization of CeCl2?
1, 2. Yeah.
Okay. I got an
SP3. Yeah.
SP3, right? SP3. Good job in the chat right there too. Right. So that's SP, SP2, SP3. All right. Okay. So we're gonna wrap up with one more example, which I'm really excited to talk about this one because this is a really interesting one. So I was actually going to cover this in module 13, but didn't, so because we need to move on. But now we can cover this one. So we have PCl5 here. So we're going to build PCl5. So we're going to talk, and while we're at it, we're going to talk a little bit about its hybridization. So So the hybridization of phosphorus and actually anything beyond in the third shell, especially all the ones that end in P something, those are kind of interesting. So what's the configuration for phosphorus? What's the abbreviated configuration for phosphorus?
It'd be neon.
Neon, right?
3s2, 3p3.
3p3. Okay, cool. So phosphorus does something really, really neat. They're really so this is a theory called I'm gonna reveal it in a second. Just give me a second. So this is what normally the orbital box diagram looks like, right? So 3s, 3p. So what happens when you're gonna hybridize these, you notice how the p orbitals are full, so you can't promote this s or this s electron onto a p orbital. So remember when you have n equals 3, so this actually dates back to module 11. If you have n equals 3, what are the possible values for L?
0 and 1.
0 and 1, and what else?
And 2, but yeah, whatever. 2.
So here's the weird part. Here's the interesting part. So phosphorus actually does promote this electron on the s orbital, but promotes it all the way to the d orbitals. So it uses its empty d orbitals to promote that s electron. So what happens? So then what would happen? What kind of hybrid orbitals are created? So you're taking the s orbital, you're taking all the 3p orbitals, and you're taking one of these d orbitals, and you're leaving the rest of the unused empty d orbitals. So what kind of hybrid orbital have you just made? Does phosphorus make? What kind of hybrid orbitals does it make?
A D.
A D, okay, what's the full name? So we already used the S. We use 3.
SP3D.
SP3D, exactly. Because you're using the s orbital, you're using all 3p orbitals, 1, 2, 3, and you're using one of the d orbitals right here. So you have sp3d. So how does it ultimately look like if you have 1, 2, 3, 4, 5 free spaces to bond? How does this molecule look like? So how many valence electrons do we have for use on PCl5? Well, there's something in the chat, but I can't read. Oh, there you go. It is sp3. So how many valence electrons do we have on PCl5?
5 for phosphorus.
5 for phosphorus. And how many for chlorine?
7 each, so it's gonna be 40.
Yep. So times 5, times 5. So 40 valence electrons. That's a whopping amount of valence electrons. So we're gonna surround it. We're gonna surround it. We know that phosphorus is gonna be our central atom. And then we make our skeleton. 1, 2, 3, 4, 5. Where do we put the rest of the valence electrons? We've already used 1, 2, 3, 4, 5 bonds. So that's 10 valence electrons we've used. Where are we going to put the rest of them?
Chlorine.
On the chlorines? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So just by using the counting technique that the counting shortcut that we used earlier, can we see that can we also see that this is sp3d if we didn't know all this theory by heart, by memory?
Yes.
Okay, let's try
By
the
counting them,
count.
right?
Okay, let's try the counting technique. So it's S. You start with S. What's next?
SP.
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 SP2.
And SP3.
And then SP3. Okay. And then what's next?
SP3D.
SP3D. Because you already used up all your p orbitals. Now you're going over to the d orbitals.
That's crazy.
Right? It is crazy. And once you kind of understand how it works, like, oh my God, what the heck? So this thing that phosphorus does, and actually sulfur does this too. This is called hypervalency. So this is when the phosphorus is going to use those unused d electron, those unused d orbitals, because it can. It's crazy. It's weird. This is why it doesn't follow the octet rule, because it's gonna be like, I don't care about that stinky octet rule. I'm gonna put that electron over on the d orbitals, because I can. Right? It's weird. I get excited with this. I'm sorry. Okay, do you guys have any questions, concerns, complaints? Do you guys want a few more examples?
Kind of confusion. I think we should cut it off here, Karina, because we.
Okay, yeah, I think so. Because I kind of, it's almost 2, and it's been
Almost
going on
3.
for a while. It's 3?
Yeah, well, it's 2:38.
Huh?
Yeah.
Oh, okay. My computer is like an hour behind. Bad.
Right. I'm gonna
But yeah.
stop recording.